So, so this talk is based on some work that I did at the end of my PhD that has been on the shelf. So I'm definitely hoping to get some ideas back from people when they kind of see this. I'm planning on starting work on it again in about a month and a half or so. It's based on an idea of a paper that we have submitted at the moment, but that was an ML paper. This is a bit more kind of application based, but it's also kind of loosely based on kind of some of the work that Bayes-N does or inspired by that kind of stuff. So I think the methods here might be pretty applicable to everyone if they're kind of solve a similar problem in astronomy. So hopefully people can kind of talk that or ask questions in that regard. But I'll show the problem that I was trying to address and talk about the methods that I developed to try address that problem and why I think that maybe it's a good idea. Okay. Yeah, so the problem essentially is that we want to infer kind of stellar parameters, okay, the data generative process that kind of describes the properties that we observe in a star, along with decoupled from the effects of dust, that attenuate the SED, and you get kind of a more dimmer and redder light curve that you might observe. But ultimately, we have this problem where we have some parameters that govern an intrinsic property of a star through stellar evolution, and then we also have some parameters which govern kind of the environment between us and that star, kind of through dust parameters. And the ultimate goal that I kind of want to kind of set this in is when we have kind of access to a calibration set that's usually kind of through, I use through kind of spectroscopic labels from high resolution spectra or medium resolution spectra. But also we have kind of a physics-driven forward model. These are really common in stellar astronomy, where we have a model that describes, from these stellar parameters, we forward model or simulate in a physics sense what the observed photometry or spectroscopy might look like. However, in general, these models are misspecified in ways that are kind of problematic. So particularly for like low mass stars, these are and post-main sequence stars, these are kind of poorly calibrated in a way that is going to be quite problematic when we deal towards like looking at really amortizable inference. And the kind of context of this is, we have a lot of data and we want to be able to infer robustly at scale all of these data parameters and dust parameters, and ideally kind of have a way of being able to interpret the robustness of our posterior and make everything quite nice. But also, while we know that these kind of physics-driven forward models are, a bit misspecified, we do know that they are pretty good at times, and we want to be able to use that information. And we also have a lot of data, and in the future, kind of with Roman and LSST, we're going to have even more data. Like there's a complete abundance of data. However, we don't have a huge, like the same scale of spectroscopic labels. So the purpose of this method is to try combine, all of this information when your calibration set is much smaller than what the kind of observed data that you expect to see is, but also use that information from the physics-driven methods, and hopefully they can, we can quantify, how wrong these methods are, and ultimately try to get reliable posterior inference. So a brief kind of flow diagram of what we're interested in is presented there, and this might be kind of similar to problems other people deal with. But the big problem kind of stellar parameter inference is that we tend not to kind of infer everything kind of at scale jointly. I mean, there's some people who are trying to do this, but kind of very crudely, we create a model template of stars, either through a data-driven sense. So this is the kind of template of what the intrinsic color magnitudes and or SED looks like of that star. And then we adopt an extinction law, which is usually generated using another data set. Then we kind of adopt priors and we do inference. But actually, there's pretty strong systematics at every step of this, using kind of different data sets, and kind of all of these errors then kind of propagate down and tend not to be accounted for when we're doing kind of scalable inference, or even any sort of inference for that matter. But these problems become particularly kind of pertinent when we're looking at kind of amortizable inference, when it's kind of a specification in the forward model. So already we have methods which kind of model, ultimately kind of we think about two modeling aspects. In the forward model, that is again, that model of what the intrinsic SED looks like, kind of before the effects of dust have applied, and then we also have models which describe dust. You know, we can involve these together, apply passbands, and kind of predict some photometry. In general, in the field, these kind of split into kind of data-driven forward models using spectroscopic labels to define these intrinsic templates. You know, there's certain selection problems with this. You know, we don't have great coverage. It usually requires kind of very high data, and this, you know, as we try to look very deep, like the depth of what we expect to see, high resolution data isn't always going to match, or high resolution spectroscopy isn't always going to match what we expect to see from the photometry that we're trying to probe. We also use these physics-driven forward models. These are hugely beneficial for a big key aspect of astronomy when we have no distance estimate through the parallax. These physics-driven forward models constrain, basically, you know, they model the HR diagram and they give a pretty good constraint on your absolute magnitude and therefore can provide a kind of rough posterior constraint on your distance. And then given that we, you know, adopt one of these methods, we can start sampling from our forward model using either like an SBI method or any other sampling method that people have been kind of talking about so far. And so there's certain problems with a lot of these. The data-driven forward models don't have the same error propagation, the same model specification that the physics-driven forward models have, but we have pretty poor coverage. However, physics-driven forward models have better coverage, but they're misspecified in different ways. So ultimately, you know, looking forward, being able to kind of use all of this information is beneficial, and it's kind of the main purpose of.
Okay, can I?
Yeah.
So I don't quite understand the difference between a physics-driven and a data-driven model. What is it?
So maybe I should say, yeah, physics-driven is where we're using stellar evolution code to, you know, first we'll sample from our prior. We use stellar evolution code and then atmospheric codes to then you sample an SED, and it's all from the perspective of numerical simulations. Of course, at some point these are calibrated, but these are basically calibrated relative to the sun. There's not a huge amount of kind of strong calibration with these. But yeah, this is physics-driven computationally, and doesn't really use much data to kind of actually define the simulation.
Data-driven model.
So the data-driven model is where you use spectroscopic line lists to define these parameters in a completely independent way. So this is using data reduction pipelines. You can get a kind of like from the broadening of your like kind of lines on your spectra, you get your effective temperature, you get your log G, you get your metallicity, and so then you learn like regression or probabilistic map from there to your SED and then convolve. So these are basically two kind of core templates. But the problem being, as I said, to be able to derive those parameters using spectroscopy, like we just don't have the data to get the coverage for our whole galaxy. And, you know, so there's benefits of both, and there's problems with both. And the idea of kind of what I'm trying to propose here is to try, you know, combine these and make everything all a big joint fit. So yeah, that answers the question. Sure.
So another question, do you only learn about stellar parameters or also about the dust?
So we also learn about the dust, and that's the big difference with what this method proposes. So as I said, usually, so the most common dust law that's used is the Gordon 2023 dust law, which uses like a very small number of OB stars. And actually the way that they propose this is pretty problematic, or the way you kind of derive this is pretty problematic. The reason being is essentially to create a dust law, you need to have an estimate of AV, and then you look at your like the color shape, and like this, propagating these systematics is going to be really important because we know like the dust law is complicated, but these systematics aren't propagated properly. And so the idea being is that, well, we know that actually Gordon 23 represents it does represent good information. So it's like, we're going to go forward and say, well, that can be like a prior of what the dust law affects. And like, let's then see what the data has. Because we have the data that Gordon uses, we also have so much more data that we can then hopefully combine and learn everything all at once. So trying to kind of extend what the previous methods look at, yeah, it's really doing something at scale. Kind of we talked about a lot of JSM and these methods is that, you know, sampling methods really won't scale for the kind of billions of stars that we expect to see. And uncertainties are extremely important, particularly when particularly in Session2 in future kind of surveys, we're really not going to have any distance constraint. So having reliable kind of, or we won't have any parallax to kind of really tightly constrain the distance. So having distance is kind of very degenerate with a lot of these other parameters. So being able to kind of propagate your uncertainty is important. Yeah, the kind of Bayesian node double use of data, this is kind of common in this field where, you know, you can use, quite often people use like reddening values or extinction values that use parallax that then use parallax again to define their models. It could be quite problematic. So we kind of want to go forward using all of this information, but trying to kind of, now that we have the machinery to learn this stuff, to go forward with good principles and yeah, try to learn everything all together. So this method was kind of coined, and Stelliformer I came up with, I think, yesterday morning. I don't know if that's going to be actually the thing that happens. But actually the method this is based on is a paper called Robust Variation on Neural Posterior. So this is just kind of a punchy name, like Robust Variation or Posterior. Took up a lot of slide. So sorry, the slide's a bit small, so I can kind of zoom in to show what happens, but parameters aren't too important. But the kind of motivation is, yeah, can I use the physics-driven methods as a prior, or my SED, and then see what the data says about the SED and the dust all together. You also want amortized inference because, yeah, things are scalable. But importantly, we want to answer both the inference problem and the modeling problem at the same time, because we know that the SED models are poor to some degree, but the data is going to tell us a lot about that SED, and vice versa. If we have the labels, we should also be able to learn the posterior at the same time. And I'll briefly just say, like, another thing that's kind of important for this is what makes you trust this posterior. So there's many people have talked about coverages and things like this, but ultimately, like when we talk about NPE or like neural posterior estimation, if you kind of hand someone some samples without any sort of metric to justify what that looks like, you know, it's very difficult to trust it unless you can, you know. But we tend to trust, like sometimes we can trust sampling methods where we have a defined forward model because you can look at your posterior predictive and have, or maybe not trust, maybe trust is the wrong word, but you can interpret what your posterior is doing through your posterior predictive and look at how it fits that model.
You can see if there's a reason not to trust it.
Yes, maybe that's a better way of putting this. Yeah.
Well, because it's not about the model, it's comparing against the data.
Yes, exactly.
Comparing the fit against the data.
Mm-hmm.
But you're at least seeing if it's consistent.
Yeah. So there's a whole nother story about what happens on the posterior level, but ultimately, yeah, can we then go back and see if it's consistent with the data?
So why do you have only some of the, I'm sorry to interrupt, but you have X's in some of them, but not all of them?
It's a good question because this is what I like about this paper is because so we don't want to double use data. So a lot of the extinction values already use parallax to get estimates of at scale, right? So for us, this doesn't quite make sense to then have this as a true value because that value used the data from someone else's processing. However, what we do have is Planck data, which will, in theory, tell us what the integrated extinction is out to infinity. So what you have for extinction is an upper bound through AV. So ultimately, this is what, like, the extinction of the extinction law is a residual relative to what you learn through your stellar model. So in some sense, there's no true value, but we have an upper bound. Now you can probe these things in different ways through, like, you know, we can feed this information. People try to find integrated upper bounds through, like, you know, H1 emission or through what the Planck data is doing. But ultimately, for us to use a defined value at that point, it means that you need to then assume a value from someone else's data that used your data, which is a bit of circular.
This is just for comparison, right?
Yeah.
Plugging it in the network.
So yeah, I mean, in theory you can, but I left that in there for some of the spot.
I can ask you the question.
Yeah, you want to ask another question?
No, so that someone can ask you this question.
Yeah, exactly. That's exactly what I left it. Okay, so big random flow diagram of what's actually going on here. So you have your observed data. So each kind of part of this will kind of talk about, you know, encoding certain desirable properties. So we used You can then like pass this through a masked encoder. The reason being is that you're going to look at, you're going to have very sparse data, particularly when it comes to parallax measurements. So ideally, you'd like this to be able to work from any given data set that you put in, and you want it to be kind of consistent. You want your error bars to, you want your posterior to kind of inflate and all of these different things. So kind of very crudely, without any logic, we use we use some tokenization and a transformer encoder. I can go into that a bit more, but again, my memory might be, this hasn't been looked at in a couple of months, but I'll try to do my best to explain if anyone has some questions on that. So this works as an embedding to the input of a kind of normalizing flow. And so this defines your variational posterior. And so this is kind of, in some sense, it's just like an like a variational autoencoder model, right? So you have a variational posterior, and then you also want to have a decoder model which learns your SED and your extinction law at the same time. And through your posterior predictive fit, you can kind of match the data. So the kind of, there's some Bayesian inspiration here of kind of like using the, what you can do is
You might be over-assuming that people know what Bayesian is.
Okay. So
in a couple of decades, right?
So how you can, well, then I'll say, how you can model the kind of forward model. So ultimately what we want to do is learn the posterior and the forward model at the same time. And so the better your posterior gets, in theory, the more information you have and more reliable information you have to then learn the forward model. So to model the forward model, we use just a spline and wavelength sampled very finely. And then there's a neural network as a function of the effective temperature, metallicity, and log surface gravity, and an extra latent, which I'll talk about in a minute, which then tries to predict the intrinsic SED. You then also have an extinction law, which you've tried to learn, and that has only, for this model, only has an AV and an RV parameter, and that's also represented by spline. And so then you try to kind of recover the posterior predictive. Yep.
The difference between a forward model and a posterior is that the forward model is the spectrum.
The forward model, is a spectrum, and it's a deterministic function. So like there's a Gaussian, I'll explain, I have more equations which can kind of put this in a bit more context, but essentially being is your forward model is a Gaussian likelihood where you have a function which is a cubic spline, a function which is a neural network which outputs the cubic spline knots of that SED, and then you have like Gaussian noise on your observation. So it's like a regression task in the forward model with a Gaussian likelihood. We're trying to learn that neural network.
In that case, how is that different from the posterior?
So the posterior takes the observed data and plugs it into a normalizing flow, and then you can sample, and then it allows you to sample from the target parameters of interest, which are your effective temperature, log gravity, surface gravity, and your extinction parameters. So I have an equation here. Yeah, okay. We can look at the equations to make things a bit simpler. So you have a function which represents your forward model SED, and then you also represent a lambda as like, again, these are all just splines. And then you can, convolve your passbands to get predicted photometry. So everything here is free, essentially, free parameters.
And this is specified, or is this a chain? Because I think you have two of those, right? So you would have something pre-trained that you do the likelihoods for the VI from the previous slide, right?
So everything's trained at the same time.
Yeah, but you would have one which is kind of fixed. It's before you start, you have this model that you built and you know the function, right? Is that true?
No, so what we do, do you mean like this physics?
Because if you go to your previous slide, there's this one, right? So there's a variation of posterior, and I guess you train this using a likelihood.
So this is like autoencoding. So so the likelihood that you are using is not fixed, it's trainable. Essentially what you do is you use like an NPE loss to anchor what that latent space looks like. Because what actually happens in reality if you just let this go, your latent space can just become whatever it wants, and it's not interpretable. But the NPE loss regularization, so this is what we were talking about yesterday, is kind of like in some sense like a Shannon-Jensen loss. There's like
But the
forward loss.
MPE is trained or on what? On
It's trained
real
on-
labeled data?
On real labeled data.
Okay,
Yeah, with the same
I
encoder
see.
input.
I see.
Um,
There's no explicit likelihood in a way. You've just trained an MPE, let's say, on some simulations from the universe in which you know. Okay,
but then
I
I'm also
understand.
learning the likelihood and the
understand.
posterior at the same time. So essentially, this is what I'm
I understand.
positing that the forward model is.
So,
Yeah.
one more question. So, Ken, so go back to your previous slide.
Yeah.
So when you have this posterior predictive as a function of wavelength, that where is your photometric points? Or the part of this?
Your photometry is in your observed data, and then but it's also in your
Posterior predictive.
it's the conditional on your posterior, and then you observe it then in your likelihood. So if I go to this equation, the bottom equation there is how I predict the photometry. And so that's like a latent photometry, and then I have a Gaussian likelihood with no measurement error to compare that to. But
So
I also
you constructed your F lambda ops as part of your autoencoding.
Yeah, and so I also have that as a direct conditional into the posterior. And so if I look into what the kind of variational distribution is what this is essentially what is happening. So you have some transformer which is encoding your data along with some masks. It then compresses that into a context vector, and then you have a variational posterior over kind of your both your kind of extinction parameters and your stellar parameters.
So you don't allow extra stuff.
So this
You
is
just wanted to encode exactly these 3 parameters or something.
yeah, and I'm kind of I think
6, 7, 8.
the reason being is that we really wanted to couple extinction and the dust law from the other parameters, because without this, then there's like it could be very hard to isolate in latent space which is contributing towards the intrinsic SEG. Because ultimately, like down the line, you want to use this for like dust inference, but actually you don't want this to be tracing some other correlator through a latent variable.
There was a paper by Uroš Telak about supernova embedding. Do you remember the name? Which was doing some autoencoding again, and it was like aligned with some of the known parameters, but then some expert of known.
Yeah, I forgot.
I'll find that.
Stein, George Stein.
Yes, yeah. Anyway, sorry.
But when you data fizz, are I mean those? Do you have a calibration set where those are known or?
Yeah, so
okay.
they're like the TEF, log G,
Right.
metallicity, and yeah, they come from like some spectroscopic data set with error uncertainties in them. So you want to learn those as well. So you have a variational posterior where they're sampled from, but then the kind of NPE loss is also directly used to kind of encode that in your variational posterior.
Right. So what you're saying is when you have the spectroscopic set where you have spectral lines, you can more reliably get the physical intrinsic parameters, and they're not less or not degenerate with the dust, because dust is a broadband phenomenon.
Yeah, that's the hope anyway. Whether or not we can really do it, have that assessment, but hopefully. So the one thing as well, there's a latent. There is one latent, which is Z, which is actually a gray term, and this comes from the fact that it's very difficult to model the radius of a star, and like you need some kind of astroseismology to be able to do that, but it does matter, and so you can have that, like with some prior over it, but you should to some extent have that. So this is probably degenerate with the gray component of the extinction law, but if you care more about the extinction shape, that's not too much of a problem.
Why does the radius of the star matter for determining extinction? Or
So just because you have everything with the SED should scale as r squared over d squared. So we don't have radiuses at all. It's very difficult. So there should be some small extra gray component, like that is in your forward model that we don't have parameters for.
Okay. I think the D is very, very large, so.
Yeah, so it's
Uncertainty.
it's probably I think it's probably not necessary. So back into kind of talking about the physics of things is that this you want to be able to regularize. Like there's serious information in what these actual spectral, like the synthetic templates tell you. Particularly about line lists, which mightn't be available from kind of the low resolution spectroscopy or photometry that might be reliable. So you can regularize against kind of physical, or sorry, not physical, but so kind of assuming that this is like some sort of prior understanding of what the SED looks like. And a nice thing as well is that in theory, when you train this you can actually evaluate what this is. So you should be able to see how much the data differs from what you're kind of prior, like what the synthetic model is telling you. So yeah, broadly speaking, it's just a huge loss function with loads of terms in it. But let's not worry about that too much, unless anyone has any questions on the math.
So I'm still looking for the photometric points.
So yeah, I've got them coming up now when we look at a point. So yeah, ultimately I like this little diagram where it's like the forward model and the posterior model are both trying to like go towards the same distribution. The idea being is that they should be able to help each other. So a big thing is that we just use kind of Planck values. So it's just an upper model on what your extinction value is. But yeah, let me go into what, let's briefly look back at that posterior. So this then, after training this, you have a posterior over what this looks like, and you think, okay, let's look at the posterior predictive. So here is what posterior predictive looks like. So how you generate this is that you take all of your photometry and what we also use Gaia BPRP low resolution spectroscopy. You put that into your encoder and you can generate samples from your variational posterior. You've also learned a forward model. You put that back through your forward model, and then you can find that you can cover the photometry and the SED pretty nicely.
I have a very quick question.
Yeah.
On this. Because you call it the posterior predictive, but you don't add noise to the orange line or something like that, like the observational noise, do you? Because, okay, so each of the points would have an error bar.
Yeah.
And that's how you define one of the losses, I guess.
What's the median?
Very small.
There should be.
No,
there
I
should be
agree.
an error bar.
There should be an error bar on the points and showing it, not showing it, fine. But you do not, when you generate, right, this thing that generates from the parameters, it doesn't add the noise, right?
Which part?
The part where you start from the parameters and then you pass
it goes to the forward model.
Yeah, the learned forward model just has an intrinsic SED, an extrinsic.
So no, it does know, the loss function
noise.
does know about the measurement uncertainty. Is that what you mean?
It shouldn't, well, the loss function should know about it, right?
Yeah, it does.
Okay.
Yeah, it does.
But-
Just like against.
okay.
But he's talking about,
The prediction that you say is actually a distribution of the latent noise.
Yeah, so that's exactly what this
Okay.
is. It's just that for this example, it's just really well constrained.
No, I understand.
And so during training, we actually use like an importance weighted objective. So you're sampling K times and
Okay.
so that you can try and get the.
I
You
understand.
can hardly even see the distribution, actually.
Yeah, so the constraint is really good.
Yeah.
Now, again, as I said, maybe like this is a very, very on the shelf and young experiment. So there's an analysis which will have to be done in the near future, kind of about how well this is constrained and kind of on scale. But this is a project from the past and young. But from the examples I did back then, it looks pretty good, and the recovery is pretty nice. So that you can actually get a really nice constraint of what the intrinsic SED looks like, and it's definitely different from what the synthetic model says. So there is a small difference between what your synthetic model is and which we expect. I mean, the resolution is different, but yeah.
So we have like 1 minute.
So that's it. Yeah.
Any final questions for Matthew or? Perfect timing.
The dust curve, we have a dust.
I don't have this curve, but the bad thing is that it just currently it just goes straight to the prior.
Oh.
Yeah,
The prior being.
the Gordon 23 extinction law. Well, no, I think it's more. So I'm more the fact that again that this was done with a relatively small sample size over the space of a week in December. I think So I was talking to someone about this recently, and they said to get like this really complex distributions, particularly with like this encoder, this big transformer encoder, is you need a lot of data. So I probably, hopefully, don't have enough data.
That's great.
Only one comment. This might be the solution we were looking for the SED problem for the past 15 years or so.
Problem?
Yeah, that's the one where we have data from at different sizes, and we didn't know how to combine the likelihoods. So you bypass that entire problem by constructing one single SED.
So yeah, I think that's basically like what phase N.
Yeah.
Huh?
Not phase N.
So he's talking about this type 1A supernova SED model that we've been working
Yeah,
on.
sorry, yeah.
They don't know
I
what that
don't
is,
know why
by
I
the
think
way.
everyone.
Yeah.
Okay, we'll talk about
I don't
that.
know. I mean, a lot of the structure of what you're talking about is about that, except we use HMC,
Yeah.
Hamilton and Monte Carlo to do the inference,
Mhm.
whereas you're using autoencoders and SPI, I think. But what are you talking about? You're talking about something else.
Oh, there's something else.
Has
So,
not been solved.
so we had, talking about this very long time ago, we had this problem where, considering this problem where we have high resolution spectral.
Oh, yeah, I know that one.
Yeah.
Oh, I mean, you should probably explain for everyone else, but
Yeah, and photometric data from optical passbands and high resolution spectra from X-ray. And when you try to do a fit, a regular, model fit, it's dominated by the X-ray and it completely throws out. ignores
The data with the very low errors dominates, more than you would like it to.
Yeah.
I thought it
and
was
the
that's a spectra dominant because you have a lot more
bits.
numbers in a spectrum than you do in photometry.
The likelihood is dominated by this.
By the data,
By
where
the,
there's like a likelihood ought to be, right, but yeah.
Yeah, I
But
feel like that's
you don't
what
like
happened,
think the data should be weighted as heavily as it is.
as it should be. But I think
Yeah.
what his solution is simply to ignore it.
Throw away the data.
Well, I don't know.
No. Construct the low resolution photometric data and.
I feel like it might be the same problem though, because if we sample really finely and then you have some high resolution data that essentially is similar to you having a really small narrow pass band with low errors, I think it might also just try to converge on that. I mean, if it didn't.
No, if it does that, this sort of thing that you have up here will fail.
What?
You'll see huge differences between the photometric
Okay.
predictive.
Cassia.
Me.
Yeah, just before you were talking, when we were talking about pragmatic phase, you mentioned that method where that downweights certain pieces of data.
Oh, the cut one,
Good one, that's what that is, right?
cut base. Max
That's
could
what
talk
you
about.
want.
But I don't think we should talk about it now
Anyway,
because we are
base.
digging deeply into Max's time.
Well, he can start with.
I just finished my slide, so that's okay.
And is that gonna come up in Max's?
I don't know, you're gonna talk about the cutting, right? So
Cutting?
I think Vinay, just to preface this, when we say we're gonna throw away the non-type 1A supernovae, we can think about it as throwing away some of the X-ray data that you're like really overfitting to, but you don't trust that much because
It's like
it
you
seems like.
You reweight that part of the likelihood. I feel like maybe we tried that. I mean, this problem,
No, it's
we
not
last
gonna be
talked
exactly
about
the
it.
same, but-
5, 6, 7,
Before the pandemic.
Yeah. Yeah, we haven't touched
Before I was
upon
head
it.
of department, I think I just.
Actually,
forgot
we
what
cut
it was.
these and like pragmatic, we did pragmatic ways.
Well, I think we're just combining them.
Contamination.
I learned about cut ways,
Contamination.
Max just told me, oh yeah, what we're doing is apparently that.
Right,
That's all.
Max.
exactly, yeah, so this is a work in progress that I've started at some point doing the PhD with David, Roberto, and then Kosciuszko picked it up again this year and developed this further with Casey as well. So, and yeah, sorry about the slides. After seeing all the very pretty slides this morning, I decided I should have slides that are not as pretty now. But basically, yeah, talking about contamination in SN1A cosmology when only having photometric data set. I think everyone here has seen SN1As and how that we can infer cosmological parameters from supernova type 1As. Unfortunately, only for a small subsample of 1As we have spectra, in which case we can classify them reliably as type 1A or anything else. For most of, for instance, LSST data that is upcoming, we'll only have photometry, and given photometry, it's just much harder to reliably classify supernovae. So we will have some type uncertainties on 1As versus any other types. What we're focusing on today is the secondary analysis and how do we account for the contamination.
So non-type 1As in your data set.
Exactly. So there's type 1As that we care about and contaminants, which could be type 2, could be type 1BC, or types that we actually don't know yet because in high redshift there might just be some new anomalous types as well. Right. Talking about 1As, Kosio gave this talk at CHASC. We have very high realism models here as an SPI. I think this is the simulator basically, where things are very well known and with very high level of realism. So if we have a type 1A sample pure, things look great. Unfortunately,
Sorry, it's very wishful thinking, but
let's
assume that we can model some part of the data.
compared to this question mark that we have. Because now if we only see those slide curves, we have to somehow type them. For some of them we might have redshift, for some of them we might have a spectra, in which case we can reliably type them. For most of them, we can guess using a classifier, for instance, to get the type. So in this sketch, kind of just showing in one case, we have this very nice model for 1As. In the contamination case, we really don't know anything because there could be various types, again, that we don't even know. So what do people do right now and what can be done? I mean, from first principles, one could fit a fully Bayesian mixture model. That is basically from the light curve data, one could go through all the way through, have a 1A and non-1A model, do everything fully Bayes. Then the second, what people also do is just fitting a classifier, taking the type 1A probabilities or scores, and given some thresholds, they define the sample as 1As or contaminants, and then just fit on the 1A model. And this first one, pragmatic modular or cut approach that we are introducing now, basically. So I want to show on a very simple toy example why the first two cases might fail, even in very simple, in the very simple case. So we should also expect that it will fail in the more complicated cases that we will observe. So let's have this simple mixture model, just 1As with observed magnitudes and redshift. For the type As, we have some very narrow scatter. I will show this on a Hubble diagram on the next slide. For contamination, again, Gaussian, same structure, but we have some increased scatter. This is a very simple cosmological model where we only have omega m. And everything here is kind of very basic. We can compute the true posterior class probabilities just with this ratio, which we'll use in the analysis, but I will talk about this in the next slides. So, okay, if we are fully Bayes, we fit a fully Bayesian mixture model, we update the type probabilities based on data that we observe, on all the data. And in the case where we have a low scatter contamination model, this is great, right? So this purple is fully Bayes. We will have information from 1A, from the 2s, if we have the correct model. That would be perfect. Which is much better constrained than the 1A only model. We can see if we just don't care about contamination at all, we would be very biased. In this case, we should be fully Bayes.
Because you can separate them easily.
Exactly. Yeah. So if we had a good model for the contaminants, if they were well constrained, if they were low scatter, we could separate them easily and we would get information from both populations.
So does the scatter have to be low on both of them?
Yes. Yeah. So
we separate it.
Yes, that's because you don't as soon as they separate, as soon as they overlap.
Exactly. Things get worse. We can still get information, so that's what I'm showing in this lower one, which is still unrealistic, but more realistic that the contaminants are much more widely scattered. In which case, I'm not sure if I can exclude. So basically the purple posterior is still better constrained than the blue one, which only fits the 1A. So if we had the correct model, we can still get some information from that high scatter.
What's the orange curve? Is that all objects?
Orange would be just fitting the 1A model to all objects.
Oh.
Exactly. So,
but the other ones don't, it doesn't look bad. I mean, the orange one is bad, of course,
yes,
but we're not gonna do that. Am I missing something?
No, that's what we
No,
were
that's
working
exactly
for.
what
That's Max is building to,
showing right now, exactly.
should you care?
Yeah, exactly. So this is just why should we get fully based is good as long as we have the correct model. It's okay if there is large scatter, we don't really gain that much, but if we have model misspecification, fully based fails. Right? Because even in the simple case where we just have this, so if the data is actually generated under this Gaussian, which has some redshift magnitude trend, which might be the case, we don't know. For the contaminants, we still have the correct model for 1As. So you can see here, there's just more 1As down, more contaminants down here.
What's M, what's capital M? That's the magnitude. So is this, the model at the top is the model for the contaminants?
That's the contamination model.
So it's, you're just saying that other model is not, that using the same model is not reasonable?
Yes.
The mean model is not reasonable.
Exactly. So if the generated model, if the data is actually generated under this shift, but we fit a Gaussian, then in the fully Bayesian case, we are just confidently wrong due to the model misspecification.
Confidently wrong, that's bad.
Right.
I'm confident and wrong.
Exactly. So in this case, we are, we shouldn't do that because we don't know anything about the contamination model, and we are probably wrong about the contamination model, right? So fully based modeling both 1As and contaminants might not be good, and we shouldn't rely on it. The second,
But we wanna point out that we're still not worried because we can still kind of discard them based on the classifier, right?
Yeah.
So this other green, I think,
if you
curve
could-
is still fine.
Yeah,
Somehow.
that's the next point. You could still, basically, if you use a base classifier and you just take 0.5 as your cutoff, take everything else as a 1A and fit the 1A model, it still works well. Because they just look the same, they're overlapping and fine. But
So that's the black and the green at the top, right?
yes,
The two
exactly.
that are the closest.
Question.
Yes,
Does it depend on number of contaminants?
it
Small
does.
versus-
exactly, yes. So it's basically the threshold is arbitrary with the proportion of contaminants versus
Okay.
1As. Exactly. That's exactly. Now, black was the only 1A, so if we had an oracle that tells us which ones are the 1A, which ones are contaminant,
That's bad.
green, exactly. Green is the cutoff at the base classifier at 0.5, and purple is the fully base, which we just showed. Might not be reliable if we have model misspecification, which is likely the case. And then the next part, which is quite interesting, something we just actually found this week. People do just taking cuts, and what they mostly worry about is how many contaminants do we still have after the cut. But what one actually should worry about is how many 1A do we actually cut off, because what we do is basically introducing a similar effect in Malmquist bias, and you can see it on the left side here. So if you had this overlapping distributions of here, blue is 1A, the contaminants are in orange, and down here are color-coded based on the predicted types. So blue are predictions for being 1A, red are type 2. And what we see is that a lot of actual 1As are cut off here based on this, base classifier threshold as being type 2. That's the similar effect that we see for Malmquist bias, that the just fainter objects in this case would just be classified as type 2, just due to the overlap of those distributions. And that's very arbitrary. So in this case, we would get a very biased inference on the 1A as well. So that brings us to
The threshold, so that's the one that in the previous slide looked good.
Yeah.
So I mean, can you say, what is different about this one versus the previous one? Because you were threshold.
just more overlap here, and we have a higher proportion of 1As for high redshift 1As.
So they're overlapping in the wrong place or something. The nature of the overlap.
Exactly.
The location of the cut. So basically the cut evolves with redshift because the proportion evolves with redshift.
So
And you get the same probability at a different location in the distribution of lines.
we basically have different redshift distributions for the contaminants 1As. So the rate changes over given redshift. in which case, yeah, we have a stronger cut into the low magnitude or high magnitude 1As.
So we tried to make it contrived, but with as little like moving pieces as possible. So the only moving piece here is the rate. So there is no actual magnitude drift. So the normalized distribution doesn't change with redshift. It's just that there are more a priori, let's say, contaminants at high redshift, which means that you need to cut more strongly because the prior enters, and I show the equation, but the prior enters into the posterior probability, which is on what we cut.
If you imagine that type 1As and the other ones were all kind of uniformly distributed in the universe, then that shouldn't happen. Is that?
But they actually have different rates. So the 1A rates seem to be different because they, from some studies, they're kind of more biased towards younger population than the other contaminants.
And the younger stars are nearby.
Sorry?
But it's about nearby, right?
It's about basically how many stars you have at a given time that are available to explode at 1As versus non-1As. And I think if you, maybe this or the opposite direction, it doesn't matter in which direction it goes, as long as there's like a drift, drifted redshift. I mean, this is, I don't know if you're using the real rates that we had here.
In this case, no. We use later for the other example. Okay. This is not just some.
Okay, but the rates, we have two different rates and we can check what happens
exactly inside. And this is still very simplistic as we just have one contamination population. In reality, there are several overlapping. So it will be more problematic than it is here, and it still fails.
So is the moral of the story you should be using stratification?
No. In this case, you made me lay down before, haven't you? We might have to use it for the covariance part, but we are not there yet. So the moral of the story is, what I want to talk about now. So basically going back to kind of the schematics is we kind of do not want to model all this part because it messed up. And we want to be more principled about the classification than just having a threshold. So this is what we thought about. So basically now, just about the notation. These are data. We have the labels L, which are either type 1As or Bs. We have those parameters gamma, which we just basically divide in three sets. The cosmology C, which we care about, the gamma A, which is the other parameters that govern the 1A model, and gamma B are just the contaminants parameters. Then the full posterior, we need to marginalize over the labels. So we have to write it as conditioning on the labels. L, then, I mean, this could be used for fully based, for instance, which I've done before. But now we want to use a classifier instead. And first of all, we should care about this marginal of the labels given the data. Because in general, if we had two different cosmologies or rates or just general population parameters, given those two different parameters, gamma 1, gamma 2, that might differ. So the question is, how can we actually use a classifier to replace this marginal distribution of L given D? And the justification that we have here is, say, consider the marginal. If we now integrate over all the population parameters gamma, then having a large sample argument, basically, if we
C, right?
Okay, C is
gamma. Okay, yeah, sorry.
C is including gamma. For a large sample argument, this gamma given D, just the posterior, would converge to some point mass at the true values, if D is the data that we observe in the universe. So gamma T are just the parameters that govern the universe. And that is exactly what we train, but what we do by training a classifier, if we train a classifier on real data. So let's say we observe labels, that is the spectroscopic labels of 1A versus and contaminants for some realistic supernovae and the light curve, then training a classifier on that training set is exactly conditioning on the true parameters because it's real data. So this is basically the trick to say, well, we can approximate this by using a training set observed. And now we can use the type probabilities from this classifier, and we have to talk a bit about calibration and so on, but we'll get to this later. And now we can replace this marginal distribution with this classifier approximated type probabilities. And yeah, I mean, we can show we still get consistent estimators of the posterior. I don't want to go into this much, but that's basically the argument of why can we actually use the classifier type probabilities in our mixture model. But again, not only do we want to use the classifier type probabilities, we also do not want to use the contamination model. And that's what we show here. So if we have full posterior conditioning on the class labels, we can just write basically our data separated in data given the labels are A or data given labels are B. So this is DA and DB. But DA, so the data for type 1A only is only conditioned on gamma A and C and is condition independent of the parameters for gamma B. And now the important part is that we can assume, as we've seen earlier, or actually impose on the model that the likelihood for B for the contamination model is constant as a function of cosmology, which is rather realistic as we've seen earlier, it's very widely scattered, plus we don't have a model. So we just, we have this as a function constant of C, in which case it's just proportional, so we can drop it, which we do in the next step. So basically, if we marginalize just over gamma B, then our joint posterior of the 1A population parameters and cosmology are do not depend on the contamination modeling, as this is not proportional and struct off. So that's great now, because in this case we can just sample from our classifier. We get a sample from the classifier type probabilities, and basically we marginalize over the types by just doing some Monte Carlo averaging. That is, you sample from the type probabilities that we get from the classifier, we fit the 1A model and get a posterior, and we average over various draws from the classifier, fitting the 1A models together, right? So this is basically the new posterior approximation that we have.
So you get, all of this is justifying the pragmatic posterior distribution.
Exactly.
It's not the, I mean, in a different way, because you, I mean, it's obviously the right, there's this thing that's the right thing to do if you knew this other model, which you don't know.
Exactly.
So
And that's, so I think that's,
I guess there's this other thing you could do. Okay, so there's the two things. There's the right thing to do if you knew the right model for the contaminants, but you don't have that. There's also the right thing to do if you knew which were the type 1A exactly, then of course you would only use the type 1A.
Yeah.
So it looks like this is maybe, it's like almost like a maybe unbiased estimator of that thing. Maybe
Yeah,
unbiased
it is,
estimator.
I actually showed that it's implied, yes.
So can we think of this as a summarizer which just throws away part of the data?
Yes, I
And
think
it
so.
throws away exactly the non-1As because it's conditional on the labels.
Yeah, I mean, but you don't know the labels, so it's doing it.
So
Every
depending on
time,
the
every
problem.
time you do this PM,
Yeah.
you actually assume that you know the labels. Like
Right.
for every,
Well, you're averaging over the label. You're averaging over the uncertainty in the labels.
yeah, well, basically, each of these objects is assuming you know labels and you're like Monte Carlo integrating this, right? But exactly like in normal Monte Carlo, at every step you assume you know the parameters and then you assume you know some other parameters.
Seems like a magic here,
What?
like a
Seems like
magic that you get the solutions like that, you know, even the labels are.
I think it all depends on the crucial assumption, I think, that the posterior in the end is gonna be a delta function. Well, that's, we assume
But
that the
that's- no, but
posterior
that's-
is.
that's- No, but that's the step before, right? That's
Yeah,
just
yeah, at one
justification.
point,
We could still do, I mean, that's just justification of using the classifier type probabilities.
and
So that's an asymptotic argument.
Yeah.
Exactly.
and for why they
Which shows
separate.
that asymptotically we still have a consistent estimate for posterior means, for instance.
Can you talk about maybe why you're contamination model is independent of your cosmology. Does that work? Or like, is it a fair assumption, Strauss?
It's kind of fair, because it's very highly scattered. So it's
It makes sense if you talk a little bit about why the type 1As do depend on the cosmology, right? It's because they all have this, the apparent magnitudes and the intrinsic magnitudes are a linear combination of each other. And because of that, you can get, if that weren't true, you couldn't get any information about the cosmology from them.
Not any, you can standardize anything.
Yeah, but that's the case. I mean,
You get
obviously,
less scatter. You get less scatter. So the correct thing would be, okay, you have these two data sets. Imagine that now you set off to observe 1As, do your analysis, get a posterior, now you set off to observe the other kinds, you get your posterior, and one of them is gonna be gigantic. And when you combine them, you're gonna get basically the one from 1A.
that's what.
That's what the assumption
It's
is.
the blue curve is only 1A data, and even though this is just 40% of the data, adding the 60% of contamination with the high scatter doesn't really constrain the posterior well.
Assuming that it's
That's-
assumes that it's scattered, basically.
Exactly, yeah. So this, yes.
But Max, I think I mean, we don't need to explicitly make the assumption that the data that we're discarding does not contain information. We can just say we discard it anyway.
You discard the data and you lose information.
Yeah.
If
If
it is constant, then you don't lose information.
Yes.
Yeah, you'd like to be, maybe you can argue that you don't bias yourself.
Exactly.
Yeah, exactly.
Yes.
Yeah.
No, I think that's
Well, I mean, it's called type 1A supernova cosmology. We want to use the ones that we think are type 1A cosmology. It's not all of supernova cosmology, right?
Yeah.
All, yeah, so that's why we're doing it.
in fact,
I have a stake in that field, but
I mean, we were actually thinking about,
you could the mixture of different, so in fact, if you had, for instance, 3 subpopulations and you would know 2 of them, but not a third one, you could just do the same thing.
Yeah.
With the multi.
but people have used other types, like there are people who are using type 2s to do cosmology, especially for the Hubble constant, for example.
and quasars.
So when you estimate the class probabilities, what does it tend to be?
Now you have a plot of
Yes.
Around like
Do you have-
fairly high?
So that's basically.
So there wasn't much of a difference in like the widths, the posteriors for pragmatic versus
The
the
next
other,
two slides,
other
basically.
methods.
Yeah, so I can show this now, exactly. So basically, just kind of the summary again, we just sample from the type probabilities and then we refit the 1A model and we don't need the contamination model anymore to get the posterior cosmology. And yeah, now instead of having the simple toy example, we made simulations for a bit more realistic study using some SM Cosmo light curve simulations, simulating light curves for 1A and type 2. And then we used some GV-boost to just classify the light curves using all the bands of the light curves directly plus redshift. And this is the contamination that we found here and the 1A probabilities. So there is quite a bit of contamination still remaining after the from the fitting. So this is basically overlap. We do have some true for type 2 with high confidence of being 1As in the sample. There is some overlap after fitting. And yeah, those are the posterior that we obtained. Basically here, green is just neglecting, just fitting everything with 1A model, which is far off. Blue is if we had an oracle that tells us the 1As, and orange is the pragmatic approach, which is slightly wider, but actually not much.
You lose we've seen this before in some you lose very little information.
Yeah.
I mean, how about that? You gain very little information by having actually known which ones were the types.
Yeah. So this we
The exact ones, right?
Say
Because
again?
the exact ones, because I think what you do when you resample is you do include some of the type 2s in your analysis, but you include them in exactly the proportion that is kind of keeping your distribution the same.
You're including the ones that look like type 1As.
Exactly.
So
Which-
they don't bias you too much.
Which you don't know, like.
Yeah.
And it's another interesting thing that we've looked into. So because we talked about which data should we actually use for the classifier. Because the 1A models, they only are fitted on some summary statistics, salt data, for instance, 4 parameters, for code rates. But we want to get, and we showed it, if you take the full light curve data, which gives you more information about the types, you can be more certain in your 1A model. But you need calibration with respect to the data that you use for the secondary model. So that's kind of the some characteristics of the classifier that you need to fulfill. Yeah, I think that's my last slide.
So these are the huge coupling of the parameters, the smallest parameters here.
Would you say it's huge?
I mean, also omega m versus w.
Yeah, this is a small mock.
Yes.
Okay. Oh, okay.
But this simulation.
It's not a hundred.
Yeah, this is the
I think it's 5,000 Norwegians. Yes.
So it's not just contamination, really. It's really uncertainty in the label that you have.
Yeah.
Yeah, the main, well, the point where we started from is that we will be given a classifier trained by someone, and we cannot actually touch it. We cannot retrain it. We cannot use simulations to retrain it. We will just be given, and we are given just a list of type 1A probabilities in the data release. And we wanted to do an analysis just with this. So just with this one number per supernova.
And is that, and in that case, maybe this really relates back to what you're just saying, I didn't fully track. Do you care if they use the same data that you're gonna use in your type 1A cosmology model?
They can use to evaluate this probability, they can use the same data that you're gonna fit in.
But do you worry about that? Are you using the data twice?
No.
No, because we don't update the types. Only if you would be fully based afterwards and use this as basically private
Another
public
reason,
types.
it's another it's a paragraph you can write.
Yeah.
You don't really need to simulate, because that's a philosophical reason.
Exactly. Yeah.
So the way that this classifier would be trained
Yeah.
would be on some on some collection of data with real labels, where you have gone out and asked God or spectroscopy what is the true label of a small training set.
Yeah.
But importantly, that one has to come from the exact same gamma as, right? So this is the whole assumption that your classifier is conditioned on exactly the same global parameters as generated the next data set. And so here's where we're worrying, because every spectroscopic training set is going to be selected, and it's going to be like the gamma parameter telling you the selection function.
This still assumes a representative training set, which we will have to model as well, because there will be covariate shift, which this assumption doesn't hold, but
then you can do your strat.
exactly. Then no video has a deal.
Yeah, I mean, he left the moment that you said we assume that the moment you showed this slide, I think, is that we assume the posterior is this delta, he left.
How do your final results compare to if you just use like some threshold cutoff? Or what if you made it like 85 or 90% instead of 50%? Because it seemed like most of them did have pretty high class probabilities.
I still have to, they didn't differ that much in this simulation, to be honest, but it's still not realistic. So this is just one contamination type, and that's something we still have.
I guess what your hope is that this is more robust to a certain kind of difference that is unknowable. Really.
Exactly.
Yeah.
Exactly.
I mean, you're showing that from simulation. It might, I don't know if you can argue that it's more robust on principle, but.
Yeah.
And there is this example where it's engineered to be wrong.
Yeah. I mean, at least that shows that's a reason, right? Yes, that's kind of sufficient.
A very simple example as well, just without looking at the simulations, is really the proportions of 1A versus non-1A, which then makes the classified threshold just arbitrary. As in, if we have the proportion of 1A, basically just reweights this part. And then a 0.5 classifier could lead to no 1A selected.
So that pi A there.
Exactly. So pi A and pi B. Wait, exactly. Yeah.
Anything you want.
Yeah, exactly. And this is actually realistic. So we have seen some of the simulations, they, for instance, have 40% 1A.
We're in a hat.
So in reality, I don't think in supernova cosmology, at least practitioners don't prefer to use that last bullet point, right? That's entirely based on the position of the supernova on the Hubble diagram, right? Whereas usually we trust classifications which use data which is not directly tied to the apparent magnitude, which is tied to the distance. We prefer to use this as independent information, like for example, the light curve shape or colors where the apparent magnitude normalization has been taken out, right? So we're only classifying based on the shapes and the colors and not how bright something is, because how bright something is directly is tied to the distance, and that's tied to the cosmology we're trying to infer. So in a sense that the conclusions you draw from simple toy example where your entire classification is based on the apparent magnitude at the particular redshift, all those effects are a bit exaggerated because when you include information that's like distance independent, which is the colors and the shape of the light curve, that's more robust to cosmology, right?
Not necessarily. I think you can get the same effects with the other cooperates. I haven't done the simulations, but I wouldn't. Yeah.
Well, that's the whole point. That's the whole point why a lot of the classifiers used in cosmology specifically take out the apparent magnitude, only classify using the colors and the
Actually,
micro shapes.
So this was
So
the
that-
whole discussion that we had when we were walking to that cafe. So what did we say? If we shouldn't be discarding any of the info, right? We should put in the full data.
you lose information, and you want to be calibrated with respect all the data that goes into your secondary.
Yeah, so we wanted to check some basically some coverage or some conditional classifications that they still held whatever data you use for the classifier. You wanna basically check that it still gets conditional coverage based on the parameters that we're gonna put in the Hubble diagram.
which
So
includes
X,
the
E, and M.
Well, I think it's interesting if you for a given supernova, you do a classifier that is, say, apparent magnitude independent information versus including the apparent magnitude, right? And compare the results using, say, the partial information, which is magnitude independent versus all of it, right? The reason is because the reason we often use classifiers that are not trained fully on real data is because there's not enough real data, right? So they use these simulations of supernovae where you have multiple types being simulated, and then to do the simulations, you need to assume some fiducial cosmology.
Yeah.
If you would only train, for instance, on the salt or the stretch and color corrections and redshift, you could get the same example but with different magnitudes. So you would put it on a very off of your Hubble diagram.
Yeah.
In which case you'd be very wrong because it's an outlier. So I think not including the magnitudes in your classifier might actually lead to more outliers. Because
Right. So
if it looks the same, you will just have data that is basically replaceable. And as long as it looks the same.
Yeah, but so we talked about this in the field. There's classification based on type 1A and not type 1A, right? And then if you get it wrong, you get contamination. But in practice, in our field, at the time that we're fitting the cosmology, we also have an outlier model, right? So that's what Beams does. It says, oh,
we don't need this then.
Yeah, that's my point. Is that in this method you can these things which are currently being treated as contamination versus outliers are actually two sides of the same coin.
I think
so. But when you explain this to people in the field, they realize, oh, we're taking into account outliers at the last step of the pipeline, and then the contamination is taken care of at the classification level, which uses some simulation-trained classifier where they had to assume some fiducial cosmology, and to be independent of that cosmology, they had to remove.
In this case, it
some
makes sense
information.
not included, right?
Exactly.
You need to train
So
on
every talk, we're getting another 5 minutes behind.
Oh,
I
yeah.
blame the chair,
Who is the chair?
but I think we need to give Amanda the chair.
I'm
The mic, maybe the mic.
Yeah. Interesting. So this is in preparation for LSST, like.
Yeah.
right?
So I thought Max would do whiteboard first, and I would be not alone in this. But I promise I've written it out, so it's not going to be a mess. Okay. So I'm just having a problem fitting Weibull distributions essentially. And it's difficult, it's really easy conceptually, but all the graphs are much worse than just a cartoon version of it. So I'm just gonna really quickly introduce the problem and then show you what the two ambiguities are. So I'm working with fast radio burst data, so event-based data, just timestamps. And I know when I'm looking at the sources and when I'm not looking at the sources. So what I really want is some description. Is it gonna work?
Wait, sorry, you said timestamps,
Timestamps, yeah, like times of arrival.
but you get, I mean, these are radio busts.
Yeah.
Don't you get electric fields? And
Yeah,
continuous,
They do, but they have like a peak, and they're
Oh, that's-
a millisecond in duration, so they can be
So when you say even time, the time, so somebody.
so yeah, they do have a width, and we actually have like radio data, but you can treat. And it's really short compared to the repeat.
So when you,
I like
yes,
this.
so event time is the technical function.
Exactly, yeah.
Okay.
Oh, you gotta. What you
It's a
write.
matter.
Yeah, no.
So we want some descriptions.
Uh-oh.
What is it?
It's very slow, but it's going.
Okay. I'm not gonna do a lot of writing, so it should be okay.
Sure that. if you want it.
Do you think it'll be okay? I feel like it might be confusing.
Well,
Let's see. So there's three reasons we really want this. The first is we want, so there's some repeaters that are periodic, but it's hard to say when you're comparing them against a Poisson distribution, because we know Poisson to be wrong. I'll get to that in 1 second. We want it for energy budgets. So like when can we say a repeater is on versus off, and how much energy is it outputting? Is that energy stored in, let's say, a neutron star? And for population modeling, so like do all FRBs repeat? All of these things require pretty good descriptions of temporal patterns and like population statistics of these temporal patterns. It's established from previous literatures that FRB arrival times are too clustered in time to be Poisson. So they're better fit with a Weibull distribution, and Weibull distribution is like a Poisson with an extra parameter. But essentially, so if this is the waiting times, which I'll keep calling delta t, dt, this is some, PDF, this would be Weibull.
Sorry, I may be like,
Yeah.
7 years behind on FRPs,
Uh-huh.
but now you're kind of certain that it's the same FRP. Like you're gonna like see one and it's gonna repeat, and you're gonna know that it's just this one same thing.
2% of the time it repeats, and I would say we're like 4 sigma confident they're real repeaters. Yeah. So
Because when I
Yeah.
heard FRB for the first time, there was this one, and people were kind of wondering if it's kind of repeated one time.
Oh, really?
A long time.
Yeah, there are now 91 repeaters.
Nice.
Yeah. So this is waiting time. And I promise I'll stop writing in instruction pictures. This is the Weibull PDF. And I'm sure I'm saying that correctly. These are like actual observed waiting times. And then the Weibull is described by two parameters, a shape parameter and a rate parameter. The rate you can think of like the Poisson rate, and then the shape parameter, if it's equal to 1, it's exactly equal to the Poisson. If it's less than 1, it's more clustered than the Poisson. So I basically just want to estimate K and R given my observations. The problem is that the Weibull distribution is only defined in terms of its, like for a Poisson distribution, you can either say the number of detections in some observation window or the waiting time distribution to fit a Poisson distribution. That's not true for Weibull. You have to use the waiting times.
Sorry if I missed this, but is there a reason why you think it's Weibull distributed?
Yeah, so traditional longer observations have shown that it's too clustered to be Poisson, and a Weibull distribution fits better.
Okay.
So this would be like a traditional, so like this is a timeline of a traditional observation. This would be the start. This would be the end. We detect 3 FRBs, let's say, in this observation. Call this delta T1, delta T2. You get the idea. For these two waiting times, it's really easy to write their likelihoods. It's just the likelihood, or the likelihood is just equal to the likelihood of delta T2 is equal to the density at a waiting time of T2. Even these ones are really, even though they're kind of censored, right? This isn't a real waiting time.
Yeah.
These are upper limits on, or lower limits on waiting times because we didn't see the one before or after. But even that is really, really easy to write the likelihood for. We just write delta T1 to infinity density of the Weibull. Let's say dt dt. Right, so what that looks like, and then we do the exact same for this one here, and what that looks like is if you take the probability density distribution, and these will get messier. Some delta t, you just say, okay, this is the allowed region of space, right? You know that it had, the delta t had to be at least, the waiting time had to be at least delta t1, and so you just include that portion of the CD, like basically, that portion of the PDF as your likelihood. So for a traditional observation that's long, you have a couple waiting times, you know exactly how to do this, even when it's a censored observation.
The Weibull distribution is the waiting time.
It's a waiting.
So it's like the exponential distribution in the Poisson process.
Yeah, exactly.
Not like the Poisson process, yeah.
Yes, exactly, yeah. It's even well defined if you have two correlated observations. So you could imagine really two observations really close in time. We're just not looking for 1 second or something like that. And you get two here, one here, okay. Then again, you have some T1, T2. This is delta T, I should say. T, delta T3, delta T.
I had my glasses on, so I was like, I'll pull it closer to me.
And so if you have two observations where you're not looking for a second, but they're really close in time enough that they're obviously related, this is still a really, you just know, so here, this is the difficult waiting time, of course. You know that the waiting time had to be at least delta T3 and at most delta T3 plus delta T obs plus delta T4. Right.
Maybe that's a good point to ask.
Yeah.
Isn't there a kind of selection applied to stuff that can fit or not fit within these observational windows? For example, here there should be a kind of probability that there is an extra one, which happens in that dead time,
Yeah,
right?
yeah.
In which case you have to, okay, so the probability that this happens times the two waiting times at every, because now you have like two measurements or one measurement and you don't even know if you have one measurement.
Yeah, exactly. And that's basically where I'm gonna go to next. Like, this is the ambiguity I'm having. And then it gets harder.
But that also happens if you just have one window, right? So you have a preferential selection for kind of shorter periods, which are kind of within your, I don't know, I mean, even if you have 0 observations, that's still data.
Yeah, and you can
Right.
still treat 0 observations, right? It's 0, detecting 0 would just be, it would still be that kind of upper limit on one waiting time, you would see.
Okay.
Right. But I agree, that's
Alright.
like basically ambiguity. So that's just like how you would fit a Weibull distribution. And yes, yes, you have censored data, but these are like more typical setups. The problem with CHIME is that we're in the regime of just extreme sensitive. So that's the data telescope, the data collecting instrument that I use. It doesn't choose where it's looking. It can only look at what's above it in the sky. And so for some parts of the sky, we see that part of the sky for 3 minutes a day. But we're the best FRB detector in the world, and we have 7 years of data. So there's really, like, I have to use this data. I have no control over the length of the observations, but we need a good description. So, okay, now we're into the CHIME regime here. So let's say on average, yeah, go ahead, David.
Say the most you observe is like 10 minutes per day.
There's, at the North Celestial Pole, we see 20, we have circumpolar, so we're 24 hours.
Right, of course.
So on average, we have 4 bursts, let's say, per 7 years.
Really?
Yep.
Waiting time.
It's a lot of waiting time, and that will go, but those range between 1 and 300 in 7 years.
But again, that's with 20 minutes of observation.
20 minutes of
out of
observation.
24 hours.
Yeah, exactly, exactly. And we have these really, really short observing intervals that repeat exactly every sidereal, or no, exactly every sidereal day for 7 years. And so the detections will just be randomly dropped in 4 of these windows. For the high like activity rates, we might see a couple true waiting times, but the vast majority are gonna be these like censored waiting times where we're just
Right, so that meaning that if you have to have two events in one of those little
Yeah.
windows to have an actual waiting.
yeah, and I would say that's happened for less than 5 sources.
All right, yeah.
Oh, wow, okay.
Okay, so there's two ambiguities. The first ambiguity, which I think is solvable but leads to the second ambiguity, is when does an observing window count as independent? So let's kind of draw out the problem here. Imagine you have T1, so there's some observation, and then you wait a whole year, and then you observe it again for 10 minutes, like chime. But obviously we observe every day. I'm just trying to make a point here. Okay, so imagine you didn't look at it all in a year. It seems like it would be pretty obvious that these two things would be independent. But if you wanted to like write out the likelihood for either, if you assume they're independent or dependent of each other, you would have this. So in the first case, you have this. Yeah, and you would say, okay, we know this waiting time in here is greater than delta T2 and less than delta T2 plus 1 year plus delta T3. That would be the like independent version. Or if you treat the two observations as independent, you would say, okay, we have one constraint where this is greater than delta T2, and then another constraint T where it's greater than delta T3. Okay. Now the issue here is that they give different answers, obviously. So this is like a negligible amount of probability in this tail. So if we call this thing likelihood A, we call this thing likelihood B, likelihood C. Likelihood A is much larger than likelihood B, likelihood C, because it's essentially equal to likelihood B, right? There's almost no probability in the very, very high waiting time tail. And so you're basically, these are totally separate likelihoods that you would write for the exact same situation, depending on if it's independent or dependent.
I think the right thing to do is to integrate over that interval where you don't have any data.
Integrate over the
Like-
interval where you don't have any data.
Because like.
This one, yeah?
Yeah, you wanna find the joint, ideally you had data in this whole range.
Yeah.
The distribution of this is the distribution of the whole thing integrated over the part you don't see.
Uh-huh.
I don't know how you do it.
But this is it. So
That much.
this is the integrated version, right? Oh, I keep putting on.
What is that? So you have
But
integrated.
There is some maximum likelihood we have here. It's a year after the fact.
Well, I mean, how do you know if there were 1, 2, 3, 10, 500 events in that
Exactly,
interval?
exactly.
Are you integrating over those possibilities? That's what I'm saying. You should.
Oh, you're
That's the
saying
right thing to
You should
do.
innovate from.
I'm not saying how to do it. But then the question would be, to me, would be like, which one of these two approximations is more like that?
I think you could probably write it down, you just basically say, assume that this is the distribution. These are the rate parameters, something in the Bible, blah, blah, blah. And then you have to do an integral over every single realization of events within this time window.
Well,
right? And then
again,
marginalize that.
I guess like if you, in this case, we almost guaranteed to have a burst between the two. And then you don't have to you don't care if 2 or 4 or 9 or 100 bursts happen between the two. The one waiting time you've constrained, is, right? There's no more data to fit if 10 things happen.
I mean, to me,
There is a
depending.
probability that the events have happened. I mean, you could
Yeah.
consider what happens if there's 1 event, 2, and so.
So I guess
Yes.
really what all that matters is if there is, like where is the next event? That's what matters
Yeah.
here. And where is the event, and if they're the same.
Yeah.
Or not.
Yeah, exactly, right. Yeah,
This looks to me exactly like a Feynman diagram.
a Feynman diagram?
Yeah.
Why?
It's you're calculating essentially you're calculating the weights of each possibilities. I mean, each extra event is a loop
Uh-huh.
in a node, and you have as many loops says there are, as you want to consider the number of events, and each of them gives you a weight for a particular likelihood that you integrate over the whole, or come over the whole.
Sure. You said that you cannot define the probability that there are any events within 1 year based on the Weibull distribution,
You can.
like for the Poisson. Okay, so I think that then you can just marginalize over this, you're
Marginalized, that's a better
Yeah.
word, not Feynman.
Okay, but I guess, so there's one other issue with that, and I agree that it's easy to define the probability that 1 or 2 events have happened, or whatever, just more than 2 events have happened in there to make it independent, and you can treat it as, if there's a 1% chance that no events happened, you could treat it as 1% this likelihood, right? Now, the other, and then 99% this likelihood, and that would be totally
Except for
fine.
weight.
The issue is we have mostly, yeah, go ahead.
No, so I mean, you have the rate, right, you from.
Every time we fit,
So you know what the, what you expect what are the
Yeah.
chances?
totally.
So,
Yeah, because we have a given K and R when we're fitting, right? So we can absolutely calculate and then just weight the 2 likelihood schemes such that it equals to 1, but the actual value, they have the weight of 1, but the actual value is 1, whatever probability it repeated it didn't. Now, the other issue though is that there's an ambiguity then of how many of these likelihoods we fit. Because now if we go back into this regime where we're not fitting 2 things, but instead we're fitting 7 years of daily observations, where the vast majority of these are not detected. Like, yeah. How do I say this? Okay.
Because like the way you draw it down makes it seem like linearly there's like a scale there, but really that's like 10 minutes and then
10 minutes.
23 hours and 50 minutes and then another 10-minute window. So this would be like the windows.
Exactly. And so if these are like 24 hours, 24 hours, 24 hours, and the rate is really high, then you could treat these, you could say almost certainly there's going to be a burst between each of these. And so we have for each one, just a lower limit on the waiting time. And that would give you like some likelihood to the power 3 if you had or I guess here before I wrote 4 times. If you could guarantee, let's say with 100% probability that an event went off between all of these, you would call that, and this likelihood of these 4 observations would be 4 things. But then if you have a small r, then some of them will be dependent and some of them won't, right? Like how many likelihood terms does this constitute? If it's 100%, it constitutes 4 likelihood terms, right? If it's, I'm not sure if I'm not totally sure how many likelihoods we're fitting. Because at some point, it seems like if we just detect.
No, all of them with the probability given by.
the weights of each possibility.
Okay.
Up to infinity.
I mean, it's a hard calculation.
But it might not
That's
be,
a scale.
it might, you have to kind of write it down to figure out how hard it is, I guess, is what it is.
I mean, it's not dissimilar to the pileup problem, right? I mean, you don't see, how many photons do you add that you don't see, right?
So that's what, I'm forgetting his name now.
Yeah.
The summer student was trying to do like the full marginalization by using like Monte Carlo. I don't know what his current status is though.
Yeah, I needed to see it written down to know exactly what was happening.
Because it does seem to me that all that matters is if there's 0 events in the interval between the intervals. If there's 0 events, 1 events, or more.
And if there is 1 event, then you can integrate over where that 1 event happened. Hence you integrate over where the 2 events happened, but now you've observed all of the events, right?
Right, and if there's 0 events, that means that that's another possibility. But those are the only ones that matter, because if there's more than 2, then that's stuff that you don't, they integrate to 1.
Have you actually looked at rank statistics? Because you care about the first and the last rank statistic, right? So you basically, if you sample uniformly, let's say, there's a distribution of the 7th sorted number, right? So if you sample 1 object, the distribution of the first object is here, right? But if you sample 2 objects, the distribution of the first one is kind of more towards the beginning, and the distribution of the second is kind of more towards the end. And so I think what David is saying is that you get the rank statistic, how is it called? Some statistician should know that. The distribution of the first sorted element in a list.
The order statistic.
Orders,
The minimum,
okay.
first order statistic.
Okay, and the last one, right?
The
And
maximum.
these- And these are the only ones over which you get the joint distribution of the first and the last,
Yeah.
right? And these are the only ones over which you need to integrate because everything in between is not giving you more information, but this first and the last one are giving you two intervals that you can add to your histogram of intervals to which you fit the
Wait,
the
only
whiteboard.
the first and the last like time of arrival are giving me information?
Only the first and the last one that you
In
meet.
that, in the
Oh,
interval,
yeah,
that's all
okay,
that.
I see what you're
I
saying,
mean,
yes.
if this were a Poisson process, you exactly that this is a Poisson distribution.
Yeah.
With expectation proportional to the length. You said at some, I don't know much about what these
Yeah.
Weibull processes, but you said at some point that distribution doesn't exist, I guess, for Weibulls. But I bet there's somebody who's done some kind of calculations on this.
I mean, you can definitely compute the expected rate. You just if you only use the number of detections, you lose like the clustering parameter information. So it's not that I can't estimate how many happened. It's just that I need to
I
utilize
think
data.
you need to know the probability that there was 0 event, 1 event, or more events.
Yeah.
In there, which it sounds like you
Yeah,
can compute.
yeah.
If there are 0 events, you know exactly what it is, right? Because you know all the data then,
Yeah.
it's just one interval. If there's 1 event, then you need to you might have, then you have to average over where it is. But if there's 1 event that again tells you exactly what your waiting time, the waiting time are. And if there's 2, again, you have to integrate over where they are. But that one, that's a little bit more complicated, but they're not big integrals, right? They're all 0, 1, and 2 dimensional.
And the combinatorics might become complicated.
Yeah. Well, I guess, so what happens for this window then? So I know how to calculate the likelihood from this window, because I can integrate over all the possible things that happened, right?
So-
What do I do for the next window?
I mean, here's
Well,
one,
jointly. For all of the gaps at the same time.
yeah,
So that's
But
why you're
that's
saying
more
it's a
likely, right?
combinatorial
it's a
issue.
combinatorics. The combinatorics will explore. I mean, I guess what, you're probably thinking of the same thing. You would probably add.
Maybe you're right.
Yeah,
Oh,
please
you mentioned
do.
You would
I
add,
use
you would
that.
consider, that is not, right, okay, that's fine. You might put a event there.
Yeah.
Or an event here, or an event here,
Yeah.
that would be the case of one event.
Uh-huh.
Any one of those 3, and then you just run different, what's it called, Monte Carlo processes where.
No, that's actually true. If you did it via that would be like a Gibbs sampler, sorry, you're treating these things as missing data,
Missing
you're
data.
sampling them. And then you don't have to write down you don't have to compute the likelihood combinatorically.
That is true.
The thing is that if you could, so in the extreme case, if you could sample the location of the event, then your problem disappears. You just have a beautiful Weibull likelihood. So you sample from the posterior distribution of its parameters, and now you have the new set of parameters, and you just fill in all those data points again.
Uh-huh.
My guess is that there might be you might have so much missing. You're imputing so much data that your thing might be very, very slow to converge.
Yeah.
But the hope is that you could you don't have to use all of that data. Just if there's 1 or 2 and where the 1 and the 0, 1 or 2.
Zero.
And if they are, if there's 0, there's no, you're done. If there's 1, where it is. If there's 2, what are the minimum, more than 2, where is the minimum and the maximum? And that's because that's quite a bit less information.
But I think that still has to be integrated because the location of the minimum and the maximum depends on how many there are. And because if you add more, the more are gonna be like more, and that's like you need to integrate the.
Generally,
that-
there's general formulas for the minimum and
There
the
are,
maximum.
absolutely.
PDFs, yeah.
If they're uniformly distributed over. But they're not
Then it's the
uniform.
beta.
They're not uniform.
But even if it's not, it's like powers of the CDF. So do you have the Weibull distribution in closed form? CDF?
Yeah. It has a
CDF.
it's a little nasty. but
Oh, it's not too bad.
Yeah.
1 to the, I think you could, so like the minimum is like the CDF to the power, so what power though? That's right, it's the number. No, so it's the number of observations.
It is true that like for every single window, if I have a K&R because I'm fitting a likelihood, I can simulate 1,000 times what happens in there and then use those waiting times as my likelihood.
And you average over them.
Yeah.
So can
No,
I just, sorry, no,
So I was gonna say, so I think, so there's a summer student who's working on like a Monte Carlo approach. I was just wondering if we could kind of take the Weibull process as like a way of simulating the data, add in the censoring that you know you have, and do something like simulation-based inference.
that's exactly what I was gonna say, but
Okay.
yeah,
But
I
how
think
does
it's,
it
I
look
think it's
like-
really easy.
Yes, so
So
but we
imagine
need to not
putting-
just diminish it to like the number of FRBs we did.
So,
We need the waiting times.
so you
Yeah,
would-
so you would choose different ones and use that to simulate it, and you would kind of like
If the windows are fixed.
get a.
Yeah.
Yeah,
So if the windows are fixed, you basically you get a prior on the Weibull parameters. Pick one set of them, you simulate all the events, you throw away
In
the
the
ones
windows,
which you
though.
miss,
Yeah.
you keep
Oh, I
only the
see.
ones in the window. And then that's a big list of times,
Mhm.
right, between January something and something, December something, right? And you put them in a neural network. And you just put them in a deep set neural network that some people seem to like.
you're skeptical.
I just wanna.
But I feel like it's a good
solution, so-
complementary approach to what the summer student is doing.
Okay.
But both are numerically complicated. It's not
Yeah.
absolutely clear to me that there's not like an analytical. Yeah, but I think what you'll find is that Vinay is correct, as always.
I've never been right about anything.
And that it is, you can write it down, but you'll find that there's this combinatorial ness to it. How many windows do you have?
What's 7 times 365?
Quite a lot.
Quite a lot.
See,
Remember that, like, it just might be hard to constrain the parameters of the Weibull because of the censoring is so extreme.
Yeah.
Like what, like kind of result would be like astrophysically useful to you?
It has to be a KNNR, like it has to be something I can add.
Yeah, but if you have like a lot of uncertainty on what that is, like
I think
how
that's,
precise do you need to know it for it to be useful?
I think it can be as imprecise as possible.
Could you bound it by assuming it's Poisson?
Yeah, but a Poisson distribution is in the Weibull distribution, right? It just has K
Yeah,
equals 1.
Poisson is easier to handle. I mean, you can make assumptions about where the event happens.
I bound it by using Poisson.
You're gonna get a cut out of the posterior, right? If the Weibull has a 2D posterior, by setting one of the parameters to 1.
Right.
And you're cutting, that's what you're gonna get with the Poisson. I think.
Simpler.
You're gonna get a answer, which is gonna be like a distribution over a small, like one slice in 2D picture that you want.
But that's just fitting a Poisson, right?
Yeah,
I mean, I can just fit the right, but the thing is, I
You
need
care about that
the
clustering.
clustering parameter because we these things are like quasi-periodic. And so,
Oh,
yeah, we kind of need the clustering parameter to have a null to compare periodicities to.
So this is a live telescope, or not really a telescope, but a live
Yeah, it's a
telescope. It is a telescope.
It's a big
But when they proposed this, what was the idea of how to analyze the data?
It's for line intensity mapping,
That's for something.
and we
else.
just found out that it would be really good at FRBs, and it is. It's just that this is really hard.
Yeah.
Um,
Yeah. I mean, the numerical solutions might be completely fine. It's just that it's because you can describe it so simply, it really feels like it'd be fun to figure out the analytical solution, right?
yeah. But I heard lots of words that are like, oh yeah, that sounds like something we should look into, rank statistics.
And the SPI approach would be a good like master's project. Is this,
Or
what data is
ChatGPT
this
at
using?
this point.
Is it like the public data?
Liam has all the data, but one could do this. Not sure.
This is, now we're getting off on, I can ask you later. I'm wondering about, Tribe has a lot of like rules about
Oh, right, yeah.
like people doing various service work and stuff if you're using the data and.
Sorry, we couldn't be of more help.
No, this is very helpful.
Hearing that SBI isn't completely crazy was useful, because I was pushing for that.
I think that we do think SBI is completely crazy.
Well, conditioned on wanting to get a useful solution. Or not, something to have for comparison maybe with a brute force,
Yeah.
Carlo approach.
should we move on?
Okay.
And any more questions for Amanda quickly? Okay, Yang is gonna talk about moment generating function.
If you don't mind, I represent at the front. That's
You can stand at the podium.
Oh, okay. Careful. There's a tripwire.
For others.
If you're gonna wait, I will pause the recording.
Not sure. That's the mistake.
Get started.
I can see that. Yeah, there's podium. Okay, sure. So first, this is going to be short because this presentation was made for 4 minutes. That was a strict 4 minutes for the presentation. So it's going to be the same, and it's going to be the same slides, same contents for my GSM presentation. So for any of you who missed my GSM presentation, this is your chance to revert the time flow and fast forward to the past. Okay. So in Bayesian inference, arguably this integral at the bottom is one of the most important integrals to compute, which is just an integral of the product of a distribution, a density function with the likelihood, integrating over the parameter space. And if the distribution is the prior distribution, then this integral would give you the model evidence. And if this is in a hierarchical model, and the distribution is the population distribution, then this achieves dimension reduction. But current methods for computing such an integral can be heavy for some simple problems, very simple problems, that they are almost always approximate or asymptotic. So here we propose a different method trying to cover this because I don't have a poster after this.
Send me a PDF and put it on.
Okay, it's on my LinkedIn if you prefer. So for this integral that I just mentioned, what we can do is that we can treat this as an expected value with respect to the parameter. This is, I'm just taking a Poisson likelihood as an example. And so if we substitute the Poisson likelihood form into this expected value, we get this expression. And if we take out the constant in the Poisson likelihood form, we can realize that what remains inside the expected value is simply a derivative, a higher order derivative of the exponential function. And then what we can do is that we further take the derivative operator outside of the expected value, and that's easily justifiable in this case, changing the limit. Then what remains inside the expected value is simply an exponential function. So the expected value becomes the moment generating function.
Do astronomers know what the moment generating function is?
We've been hearing about this.
only because of seeing.
Yes. Okay.
Yeah.
Okay.
Just briefly say what it is.
Yes. It is simply the Laplace transform of, for a random variable. This is simply the Laplace transform of the density of that random variable, but instead of having evaluating at the negative t of that Laplace transform rather than the t of the Laplace transform.
But it has this property that you can use it to generate moments.
Oh yes,
right.
Okay. Yes, that's a key point. So yeah, so when differentiating the moment generating function to, for example, if this t is 0 here, then this derivative, not the constant, this derivative would give you the
y moment of the parameter.
So if you take the y derivative and evaluate it at 0, you get the y moment. So the expectation of the random variable to the y power.
Yeah.
So they're kind of these like clever little things that you teach to undergraduates that I never really thought very much about, right? But then seeing found this kind of like magical use for them.
Yes, exactly. And why do I care about this in this case? Is that in counting the X-ray photons to infer the X-ray source intensities, the X-ray sources, they can overlap, and that I believe most of people here will know this better than me. But so what I can do with the MGF trick is that because this overlapping actually can be written down as a linear transformation in the parameter space. So here our original inference was for the source intensities of the X-ray sources, but what we observe are the segment counts. Segment counts in each of the 3 segments here, which I realize.
Just to another thing to clarify is that those purple circles are optical locations.
Yes.
And superimposed on an X-ray data.
Oh yes. Thank you. Yes. That was
So
I think it's it.
Yeah. So the segment counts turn out to be, like so. The sum of these two is from one source, and the sum of these two is from the other source. But this is a mixture, right? So you get a linear combination.
Yes. And for these photons in the middle, in the overlapping segments, they don't arrive at the telescope with a label saying I'm from this source or from that source, and so
it would be helpful if they did.
Yes. So, which means that what we observe are realizations of the segment intensities, and the segment intensity parameters are linear transformations of the source intensity parameters. And on the other hand, we construct a hierarchical model for this X-ray source intensity problem, and there are hundreds of sources. And if we put this model directly into a sampler, it can be quite inefficient. So what we like to do is to integrate out the source intensity parameters. But in this integral, this integral is integrating with respect to the source intensity parameters. But inside this integral, we have the product with respect to the segment intensity parameters. So which means that we can't take the product outside of the integral. So that's in the ordinary way, that's not analytically trackable. But if we use this MGF trick, what we can do is that we can actually leave the linear transformation matrix inside the MGF while taking the derivative outside of the MGF. In doing so, this trick can give us the exact value for that integral. For example, for that particular case of linearly transformed parameter problem. And lastly, this is my last slide. This method is not only useful for computing the marginal densities, but it's also useful for computing all sorts of posterior quantities, because the marginal density, they are simply the denominator in the Bayes theorem. Well, in most of the cases, the numerator of the Bayes theorem are also known. So, which means that we can simply put them together to get the posterior density. And for posterior MGF, it is the ratio of the prior MGF to the same order of derivative, but evaluated at different points. Which means that the computation is super simple for this posterior MGF. But for the and for posterior moments, it is the ratio of the derivatives of the prior moments of different orders, but evaluated at the same point. Similar stories goes on to posterior predictive distribution and posterior CDF, which means that we can compute all these posterior quantities by simply differentiate.
So most everything that Bayesians do are the hard part are high dimensional integrals. And what Sienga's figured out is how you can get rid of all of those integrals and turn them into derivatives. Now they're pretty high order derivatives. But at least in some problem, derivatives are generally easier than integrals. And at least in some problems, he's found where you cannot actually solve things with the integrals, he can solve them here. So it's like a dual, right? So it's quite clever.
And now also one point that I forgot to mention is that Poisson is just one example of the likelihoods. There are in total at the moment 14 named likelihoods that I found that this trick works, including Weibull. And
you take a derivative instead of integrals.
And well, I have to say that it works for one. Weibull has two parameters, and so you have to assume one is known. It doesn't work for one of the parameters, but it works for the other one. And actually, Weibull is actually one of the most special one among the 14 likelihoods, because there are actually different ways of doing that trick. Like one is the one that I shown just 1 minute ago, and the other one is actually you can write lots of first order derivatives and put them all together. So make sure you check you scan this QR code to check our archive script. There is a remark actually for the Weibull likelihood case. And also I have implemented a Python package. It's now the alpha version of this package called GRefractive. And it's just intended to compute all these posterior quantities and also model evidence. And although at the moment the GRefractive is not working for the multi-dimensional parameter space, but it should in principle works well for the one-dimensional parameter space.
And you want to say something about fractional derivatives? Do you physicists know about fractional derivatives?
Yeah. I know for some reason.
Yeah, it's quite strange, these things.
It's about non-local interaction stuff.
I don't have slides for the fractional derivatives.
Maybe you can just, while you go to your bonus generating function for the gamma, the order there is the value of the data, right?
Yes.
And so that's an integer. But for some of the other models, it ends up you need it's d not to an integer, but d to a fraction.
Yes. So the derivative order and the evaluation point, they are a pair of statistics that is actually jointly minimal sufficient for the parameter we're integrating the theta.
The jointly minimal sufficient statistics.
And
it's like all of the mathematical statistics names all in one.
And yes, and because it's a statistic, which means that it can be decimal. So yeah, and in particular, we have to use one particular definition of the fractional derivative called the Liouville-Carpenter fractional derivative. Other ones may fail. For example, the MGF, because MGF is integral, almost always differentiable, but not always integrable. And some of the other definitions requires first putting an integral of the MGF rather than first differentiating the MGF.
So Asian just spent 6 or 8 weeks with Josh learning how to implement these crazy derivatives into a package, right?
Yes.
So for like the Weibull, if I know you said you have to assume that you know one or the other of the parameters, but once you make that assumption, do you have like some kind of analytic solution?
Yes, like in this way, like just almost.
And then
exactly
from that, you
steps.
can get the posterior density, so it would be like conditioned on.
The other one that
you would use that to then build up a Gibbs sampler?
Could be, yeah, could be. Yeah.
Oh, for the two parameters.
Yeah.
So maybe it's a lower dimensional integral.
Yes, this is one of the drawbacks that for some of the likelihoods, it only works for one parameter, but it doesn't work for the other.
But if you could, I don't know if you thought about it. I hadn't until we were talking about just this. Like if you could combine that with traditional like integrating, like, and then still solve the problem with lower dimensional.
Oh yes, I thought that's the purpose of the introducing the trick for this problem.
Well, this one you get rid of them all. Oh no, there's maybe still some parameters you have to.
There's the hyperparameters in the problem that's still
right.
many, but of course, but yes. Yes, that's all. So, any questions?
My question is, I want to see all the fractional ones.
Yes, there will be a special talk between.
Special talk,
between us,
okay.
So.
Special thought. With more details than the rest of us.
Well, but it's okay, so let's just stick with this one. I think I asked this before, I want to. This whole thing looks very mysterious, right? And so you always ask, okay, if you believe that the beautiful mathematics means something real, which you don't have to buy that, but I do. Have you tried to think about what's the intuition here?
Okay, the intuition here is that the prior MGF, the last line here, that I'm differentiating with, is in fact underneath its mask, it's the marginal PGF, probability generating function, marginal probability generating function. And we all know that, at least statisticians know that, differentiating probability generating functions for discrete distributions will give us the probability mass at the specific points. And that's the intuition. So it's not hard to show that this is actually the marginal for whatever prior distribution you use for the parameter here. This will be the marginal PGF for Poisson.
So then that might be worthwhile to, I guess you stick with the moment general function because that's one taught people are more familiar with. Otherwise, why don't you express in terms
And this
of
is more
probability?
general, because that argument only works for discrete random variables.
Yes. Well, for continuous random variables, that's where complex numbers have to come in order to explain. Because for that PGF explanation, intuition that I just gave, that is because we are differentiating. I was saying that like we differentiate for the PGF for whatever orders and then find the probability. That's essentially the Taylor expansion. For discrete case, that works perfectly well. The Taylor expansion works perfectly well for the for real numbers. But once we introduce the fractional derivatives, then the Taylor expansion that we should talk about is along the complex, the imaginary line. So that's part of our little discussion later.
That's actually really interesting because now you remind me, because that thing exactly is the Weiss order Taylor expansion term.
Yes.
Evaluate t minus equal 1, right?
Yes.
Literally, that is including y factorial. Right? Because that's the term.
Yes.
So if that's the thing that all we should do is that people can just read out, right? You just have the Taylor expansion writes out.
Mm-hmm.
And all you need is just to read out whatever you have a table, you don't need to do anything.
Yes.
Whatever y you have, just look at which term you look at.
Yes. So I'm quite surprised that the past statisticians or probabilists didn't discover this. Yes.
Well, you're lucky they didn't. What would you be doing? And also, there's the funny thing with is it the order of the derivative or the evaluation point? You do one or you do the other, and you get the posterior, you get the moment, the posterior moment.
Yes.
That little trick.
Yes, I think I've briefly talked about this when I was describing the slide. Yes, it's that because that trick can be used to compute all these posterior quantities. And for posterior MGF, it's simply differentiating the prior MGF to the same order, but evaluating at different points, and then take their ratio. That's it for the posterior MGF. So it's simple to compute. And so to notice here is the evaluation point that differs. And for posterior moments, it's the opposite, that we differentiate the prior MGF to different orders, but evaluate at the same point, and then take the ratio. So it's the order that differs, but the evaluation point that's the same.
Yeah.
So yeah.
So it's quite clever, and so he's working on a paper. What do you call your paper? New Bayesian, a new
reimagining
Bayesian
computation.
I think that was my idea. That's what I'm saying. But it's like all of the standard Bayesian formulas are like replaced with moment generating functions.
Although, I mean, there's still limitations. For example, it only works for positive parameters and only works for 14 named likelihoods so far, but
So anyway.
Is there a generalization of these? Like, for example, exponential family is something. Like, is there something which combines these 14 likelihoods?
combine this.
Yeah, you know,
Is there a
like
common
a general family of them.
Oh, yes, we call
Like, what is the most general form
It's-
of the
it's the-
likelihood for which this would work?
It's a Lie likelihood.
that's the answer to your question. That's we call the MGF marginalizable class of the likelihoods.
It's like the Yang style, like, you don't call it after yourself?
it's someone else.
the
Oh,
D-
usually it's after someone.
Which one you ask me, which one not?
Yeah, so it's a subclass of the exponential family. Not all exponential family can it's not always
You
true.
can characterize them, but it's not, the characterization doesn't correspond to any.
So
Family.
have you thought about like what breaks, for example, within the exponential family, you said there's a subclass. What is it about the other subclass which breaks it? And how you could modify the moment generating whatever procedure so that you unbreak it?
One of the most important break in the exponential family I can see is that if the parameter is real, like it has a real like whole real line support
Instead of positive?
Yes, in that case, the MGF can blow up in the other limit, because here I only talk about the MGF evaluated as negative values. Like this evaluation statistic is always going to be negative. In this case, the MGF is always exists and is finite. But if it's a real, like whole real, that would break. The other ones, well, at least strange support for other like strange support that could also be an issue, and this is actually I have to say that this works for I show it's Poisson here, gamma works here as well, but actually beta also works here. Even though beta has limited, does it have limit? No, it doesn't have limited parameter support. But the lower limit of the fractional derivative for beta is actually 0. It actually differs from the lower limit of the for this fractional derivative for gamma. Yeah, so there are like different scenarios.
So we have now used up 23 of our 30-minute break.
Yeah.
There will be 2 more minutes. I have a more question.
Yeah.
Okay, sorry.
It's actually a serious question.
Okay.
I just suddenly realized that this might have a very close connection with the so-called Tweedy's formula.
Tweedy's formula. Oh, yes.
The Tweedy's formula using lots of derivative. I was just trying to look at it because I don't remember exactly, but it seems like because it's also using the marginal thing. So I'm sure there's a connection here.
Yes, actually, I have already explored such connection by, although I didn't look at many of the Tweedy's formulas papers, but I was reading the one written by Bradley Efron, probably one of the first if you Google it, and that actually that route actually leads to a way to derive how this formula could work to derive posterior MGF. So. But only for exponential families, because I think Tweedy's formula only works for exponential. So that actually leads to a special proof for exponential families on this diagram, on this line. So yeah, and now I have a more general proof that doesn't use Tweedy's formula. So it's kind of
so that's an alternate proof to what you have.
Exceeds it for kind of although I think the MGF marginalizable class are all exponential family members, but I mean at least there's a different proof for Tweedy's formula in this perspective. There might be perspectives or connections to Tweedy's formula in other perspectives, but I mean there's just so many interesting things to do here. So haven't explored in other directions with respect to Twitty's formula. So,
Is that it? Okay, so I say we take a break until 4. We have this ending 45-minute discussion section that we can trim that down, I think. So let's take a break until 4 o'clock.
Before we think, I just wanted to ask if there are anybody online who wanted to ask any questions.
They're all sleeping.
They should raise the hand if they want to ask questions.
No, they can just speak up.
talk.
I'm fine, just saying thank you.
Very good.
This case, yeah.
Bye-bye.
yeah, we're not-